Welcome to Get Your FRQ On. This question is from 2021, Calculus AB, question number 5, and it is not calculator active. In the question stem, we're given an implicitly defined function, and in part A, we are asked to verify that dy dx for the implicitly defined function is a given expression. So for part A, we're just going to take the expression given, use implicit differentiation, and solve for dy dx to show that it does in fact equal the given expression. So we're given that we have the curve 2y squared minus 6 equals y times sine of x for y greater than 0, and we have to differentiate this function. To do this, we'll use implicit differentiation to find our dy dx. So if we differentiate the implicitly defined function, take the derivative of 2y squared minus 6 equals y times sine of x. This implies that 4y dy dx equals y cosine x plus dy dx sine x. Notice the use of the product rule here shows up a lot on AP Calculus exam free response questions. Also the quotient rule, you just have to recognize it and you've got to be able to use it with fidelity. So if I have 4y times dy dx equals y cosine x plus dy dx sine x, after this, the goal is to isolate the dy dx, collect those terms together. Then I would get dy dx equals y cosine x over 4y minus sine of x, and that is the expression we are asked to show that dy dx is equal to. So we have successfully achieved question A. In part B, we are asked to write the equation for the tangent line at the point 0 comma square root 3. While we have our expression for dy dx, and we just need to evaluate it when x is 0 and y is square root of 3, this is really just a straightforward computation. Normally you would not have to simplify this, but it might not be a bad idea to do so. When we simplify it, we get 1/4. You do not have to simplify this. You could leave it as square root 3 cosine 0 over 4 square root 3 minus sine of 0. You would just have to make sure that either you simplify it later when you write the equation, or use that as your slope when you write the equation for the tangent line, but you must be consistent. All right, so from this we conclude that the equation for the tangent line at 0 square root 3 has slope 1/4. It has x coordinate 0 and y coordinate square root 3, so we can write the equation for this tangent line in point slope form. And that would be y minus the square root of 3 equals 1/4 of x minus 0. Do not forget parentheses when you write things in point slope form, although in this case, because it's 0, it's not going to matter if you do or don't. But just be careful. If there was a number there for the x coordinate other than 0, parentheses would matter. Part C, we are asked to find where the tangent line is horizontal given the restrictions that x is greater than or equal to 0, less than or equal to pi, and that y is strictly positive. So the strategy here would be to set dy dx equal to 0 and just solve the equation to get either an x coordinate or a y coordinate where this was true, and then reverse engineer the one we didn't find. So we have our expression for dy dx. We want to set it equal to 0. If we multiply both sides by 4y minus sine x, we get y times cosine x equal to 0. This implies that either y is equal to 0 or that x is equal to pi halves, since cosine of pi halves is also 0. However, since we are given the stipulation that y must be strictly positive, we do not need to include the possibility that y is equal to 0. You might lose a point for not showing that y equals 0 solves dy dx equals 0, but given the restriction, you're going to have to take it out. So the only place where this can be true, given the restrictions that we have, is when x is equal to pi halves. When x is equal to pi halves, we need to find a corresponding y coordinate. Well, since sine of pi halves is 1, the equation simplifies to 2y squared minus 6 equals y. That becomes a quadratic equation, which is definitely factorable. If not, you can use a quadratic formula here, and you'll get y equals 2, and also y equals negative 3 halves. But again, we're restricted to y being positive, so y equals negative 3 halves. Even though it solves the quadratic, it's not a feasible solution for this question. Now, before we move on, we have this ordered pair pi halves comma 2. We should verify that this is in fact on the curve and it doesn't involve some kind of weird discontinuity that we haven't discovered yet. So we're going to plug those coordinates into 4y minus sine x, and as long as we get something in the denominator that isn't 0, we're good. Right, so 4 times 2 is 8. Sine of pi halves is definitely not 8, so that's not going to be 0. So the point pi halves comma 2 is in fact on the curve. That point is there. It's not a discontinuity or anything like that. And as we've already shown, it does have a horizontal tangent line at that location. In part D, we are asked to determine if f has an extrema at the point found in the previous part C, and to provide a justification for our answer. To begin, the curve will have an extrema at the point found in C. Since dy dx equals 0, which it does, and if the curve is either concave up or concave down. If it has one of those flat points but never stops increasing or stops decreasing there, it won't be an extrema. So what we're trying to do here is take the point, which now we know dy dx is 0 there, and then demonstrate one way or another whether or not the curve is concave up or concave down at that point. And if it's one of those two, then we can determine whether or not it's a maximum or a minimum. In order to do this, we're going to have to use the second derivative. So we take our expression for dy dx and we differentiate that using implicit differentiation. And even though we get this nasty expression using the quotient rule, keep in mind there are some things about this expression that we already know. Because we're finding the second derivative d squared y over dx squared specifically at the point pi halves comma 2, and we know that dy dx is 0 at that point, all of our dy dx terms on the right become 0. And then a bunch of stuff will cancel. It's actually not as bad to simplify this as it looks. So if we try to simplify that expression, plug in 0 for dy dx, 0 for x, or I'm sorry, pi halves for x, and 2 for y. All right, sine of pi halves is 1. 8 minus 1 is 7. 0 times cosine pi halves doesn't matter because it's 0 times. Sine of pi halves is 1 again. So 0 minus 2 is negative 2. Continuing with the simplification, eventually we get that d squared y dx2 at pi halves 2 is just negative 2/7. The value there isn't as important as the sign. The sign is negative. From this, we can conclude that the curve is concave down at pi halves comma 2, and therefore we would have a maximum at the point pi halves comma 2. So yes, the curve does in fact have an extrema there. Using the second derivative test, we can determine that it is a local maximum.